Welcome to the talk. The topic is open source support for ARM's Mali-C55 ISP, which I hope is what you're expecting. So a quick rundown of what I'm going to talk about. A quick hello, then we'll cover what the hardware is, just very briefly, and then the work that we've done in the kernel and in libcamera, future challenges for the support, and then how you can use the code that we've written, if you have a device. If you don't know me, hi, I'm Dan. I'm working with Ideas on Board with Kieran and Jacopo. I'm fairly new, but yeah, if you don't know Ideas on Board, we're a software consultancy that focuses on the Linux media subsystem, so mostly like camera sensor drivers and ISP drivers and things like that. And then for the past year or so, me and Jacopo have been working together on ARM's Mali-C55 ISP. This is the block diagram from their webpage. It's a fairly new ISP. It's just turning up in silicon that you can actually buy. It's quite complicated, as you can see. It supports 8 different sensors streaming in at the same time, a whole bunch of image quality blocks, so noise reduction, tone mapping, white balance, and so on. And then for each input stream that you can get a couple of output streams, so you can stream, a viewfinder and a full resolution picture at the same time. If you want to get your hands on one, the SoC that you're looking for is the Renesas RZ-V2H. There's a couple of different configurations of that, and only some of them have it, so you have to be careful what you're buying. Their EVK obviously has it inside, and there's also a board from a company called IMD Tech, and they have it as well. And there's a manufacturer called Kakip, which used to be called Kakipai, although they've changed their name now, can't think why. And they have a familiar kind of like Raspberry Pi form factor board with 4 camera connectors that are Raspberry Pi compatible. And they have the SoC on, but the version they're doing at the moment doesn't actually have the ISP in it, unfortunately. We spoke to them, and we think they probably will do one in the future with it. So look out for that, because that would be quite nice. So the work that we've been doing has been taking place in 2 places, basically, in the kernel and in libcamera. In the kernel, we need a driver that runs the hardware, handles the interrupts, configures it, and tells it where to write the frames to once it's processed them, and so on. There's patches for this on the Linux media mailing list already, so if you want an in-depth look at the code, you can go and look at them, and if you do that, please send me an email and tell me about all the bits that you don't like, because kind of what we need at the minute is reviews to drive it forward. The version that's up there at the minute doesn't include parameters and statistics, which we'll come into in a moment, but those are ready to go. I just need to post them, so they'll be on there as well by the end of next week, sort of thing. What the driver creates basically is, it uses a V4L2 and media controller APIs to create the usual kind of structure that you'd be looking for if you're used to working with things in the media subsystem. So lots and lots of sub-devices and lots of video devices. As these kind of complex camera pipelines are these days, there's a lot of it. It's not just /dev/video0 anymore. And I'll just go around and kind of explain what the bits do. The top 2 sub-devices here aren't actually part of the driver. They're the image sensor and the CSI2 receiver that feed the data in. The ISP driver uses the V4L2 async framework to kind of look for those and connect them. So they need to be described as connected in device tree graphs. Then we have the test pattern generator for the ISP, which we've just modeled as a camera sensor, basically. And you can choose it as the import source by just enabling the media link between the TPG and the ISP's sync pad. And then that can output data in BIA format or in RGB if you want to exercise like the raw bypass methods that the ISP can do. And whatever frame sizes that the ISP can support, the TPG can kick them out. And you can just configure those all with normal V4L2 set format I/O controls on the source pad. As I said before, it's got 2 kind of output pipelines, and those can be configured with different formats and frame sizes. So for the resizing functionality, we modeled that as 2 different resizer sub-devices, and they just expect crop and compose selection targets on their pads to set how much crop you want to apply and how much scaling you want to apply. You can do that completely independently, so you can take a 4K input, crop one down to 1080p, scale another one down to 480, or whatever you like. And you can do that whilst the ISP is streaming as well to support digital zoom operations, as long as the output stays the same, as long as the final output size stays the same. The 2 video devices at the bottom are the capture nodes for the 2 output pipes. You can set formats on those independently as well. It supports a range of different RGB and YUV formats with a variety of bit depths and subsampling schemes, and grayscale as well. and through the one labeled FR, also raw bypass. So the ISP can take input data that's either biodata and demosaic it, or RGB or YUV data, and if you want to, you can just plumb it straight out without actually touching the image processing blocks, only through the FR pipe, not through the DS one. And forgot to mention that that's the reason there's 2 sync pads on the resizer subdevice. That's for the bypass path and the process path, and then internally the resizer subdevice uses the new streams API, routing API, sorry, in v4L2 to select which one you want. And then finally, we have a captured device called 3A stats and an output device called 3A params, and they support the image quality control loop. So user space can consume buffers of statistics from this stats device, make decisions based on the values that are in them, and then queue up buffers of parameters to the params one for the driver to consume and then configure stuff. And I want to highlight the parameters structure that we've used because it's quite novel and quite neat, I think. Normally, it's fairly monolithic, so in a lot of other drivers that do similar things for other ISPs in the kernel today, what you get for that parameters buffer is a struct that contains substructs with basically every different field that you can possibly imagine that you might want to set in the ISP. And that's where your user space fills and queues. But you don't necessarily want to actually make changes to all of those fields every frame. So there'll often also be field flags that user space can set to say, you know, update this one, but not that one, and so on. And that works fine, but it's kind of monolithic, feels a little bit clunky, and also if you need to make changes to it for some reason, that's more difficult to do because this is part of the user space API, so you can't just go making changes that will break applications that are using this. So Jacopo came up with a really neat solution that's more extensible. We have a common struct that we call a block header, and that has a field for size and a field for a type, and we can tell it what type of thing we're going to fill in here. So it can be either configuration for the statistics or gains for white balance or lens shading and so on. And then we embed that as the first member of our substruct rather than having all of those embedded in a monolithic thing. And then we can, for the structure that you actually send to the output device to be consumed by the driver, there's only 3 fields. One's size and one's called data. And you can drop those blocks into data in any order that you like, as many of them as you like or as few of them as you like. So if you want to set white balance, you drop a white balance block in. If you want to set digital gain, you drop a digital gain block in. If you don't want to set anything, you just don't drop it in. And then what the driver does is handles them with some type punning. So we interpret the offset 0 of that data member as a block header first, there, and then check what type it is, and then reinterpret it as the struct for that block and handle it. And then we just advance on for the advance that block offset to the next sort of to the position of the next block. That's what I'm trying to say, and keep going through. So I think that's quite nice. It makes it a lot more extensible. We can add support for more things. If we do something wrong or need to make a change, we can just change that small block struct rather than the whole thing, and by adding a new block type. That should make it a lot easier. So that's the kernel work. A very quick rundown. As I say, the code's on the list. If you'd like to go and review it, please do. That'd be really nice. The rest of the work has been in libcamera. If you don't know what libcamera is, I'm going to give you the very, very abridged version. Don't worry. It's a way to abstract out the complexity of those media graphs, a user space library that abstracts out the complexity of those media graphs. So rather than dealing with all those sub-devices and video devices, you can just deal with the camera. This is the kind of libcamera stack. The yellow bits are the core representations of things like v4L2 devices, sub-devices, media entities, and then frame buffers and controls and so on. But most of that has not been touched. What we've done is the hardware-specific pipelines. So each piece of hardware, each ISP that libcamera supports, needs some bespoke code in there to handle it, because of course all the media graphs are different, all the parameters, buffers that they expect are different and stuff. So yeah, that's what we've done. If you really want to learn about them, there's been much more talks in the past that tell you exactly how to implement those, so I would suggest you go and watch those. We don't have time today. The bit of code that we've done so far, mostly, is to handle the pipeline. It's called a pipeline handler, and that's the bit that does the plumbing for the media graph. So rather than having to deal with that media graph All we have to deal with, as far as libcamera is concerned, is a camera. So this is asking cam, which is libcamera's test utility, what cameras do you see? And it just tells you, I see an IMX415 and a TPG. So yeah, much easier to deal with. And the plumbing works. You can take pictures through it. Hooray. But not very good ones at this stage because it's far too dim, of course, it's far too green. So the next bit of work that we did is the image quality control loop that I talked about before. So libcamera queues buffers up to the stats node. The ISP fills those with statistics to help you make decisions on things like exposure and white balance and focus and stuff. And libcamera sends those off to all the algorithms that you implement. So far we've implemented 4: auto exposure and gain, white balance, black level correction, and lens shading correction. And they take the image to quite a good state, which you'll see later on. The algorithms in libcamera fill in those blocks that we talked about and pass them back up to the parameters, and then the driver handles those and makes whatever settings you've asked it to make. So the first algorithm is auto exposure. The way that we do this in libcamera is we estimate the average luminance of an image, basically, which we do in this case by taking histograms for each color channel that the ISP gives us in that statistics buffer, finding the average of each of them, so the average red, the average green, average blue, and then just adjusting those by some standard coefficients, and that gives you the average luminance. And then we ratio that against a target value, which we can just take from some tuning files. So that tells us, like, if the average is twice what the target is, then we need to drop the exposure by half. If the average is half what the target is, then we need to double the exposure to reach it. And then because we know what exposure we had applied to the sensor when these statistics were generated, we can adjust that exposure by the ratio to get a target exposure. And then we split that up into an integration time, so like how long the camera actually lets in light, and then a gain value that the camera can apply as well. And we bung those back to the sensor just using standard V4L2 controls. And that takes us from kind of a dim image to a brighter one. Still green and still a bit noisy, so more work to be done. The next one that we're going to look at is white balance. In libcamera, our usual algorithm for white balance is a gray worlds one, which is fairly simple. The idea is we assume that the average color of the scene that you're looking at is a kind of neutral gray, and then we apply color gains to the red and blue channels that make that be true, if that makes sense. So I'm hoping this will kind of make it a bit more clear. If you imagine that the histograms for each color channel came out like this, the means are very different. All we're going to do is shift them to be the same. It's quite a simple algorithm. It works very well whenever the assumption that underlies it is true, but not so well when it doesn't. So it'll work in a lot of ways, but if you're looking at like a big patch of green grass or blue sky, then it can have some difficulty. The C55 makes this incredibly easy. In some, it can be quite complicated, but the statistics that the C55 gives you for white balance are the average ratio of red to green and the average ratio of blue to green. And then what it expects back is a gain value to be applied for each color channel. So we can just fix the green gains at 1 and then invert the ratios that the ISP gave us for the others. And that's it. It's not quite 4 lines of code, but it's also not a lot more than 4 lines of code. So really easy. And that takes us from a kind of greenish image to a more balanced one, which is beginning to look not too bad. The next thing that we tackled was black level correction. So if you take a picture with a lens cap on a camera, you would expect all the pixel values to be 0 because there's no light hitting the sensor. But because of electrical noise, basically, that's not actually true. The sensor will say that it's still seeing some light when it isn't. And you have to correct for that by telling the ISP how much noise the sensor is picking up. You can sort of take tuning images by taking an image with a lens cap on, or somehow or other covering it, and just taking the average value for each color channel. In this case, I actually managed to find the values in the datasheet, which is why they're all the same, which is a bit miraculous, because I have never found them in a datasheet before. libcamera has tuning files for each sensor. They're just in a YAML format, and you use them to tell libcamera which algorithms to use for this sensor, and then any other data that needs to be passed into it, basically. So here we're saying, run AGC, run AWB, and run black level correction as well. And by the way, you need these values when you do that. And then the actual algorithm just parses them out and then fires them off up to the ISP. So it's fairly simple. And this takes us from a noisy black. I'm not sure if you can see it very well on the projector. On the slides in the computer you can. This is the black patch on a color pattern card, and it's like visibly not black. Not so much here, but on the laptop it is. And that takes it to a much more calibrated color. Although it still looks very dark. That one doesn't look quite as dark on the screen. Come see it afterwards. From there, we went to lens shading. Lens shading correction, sorry. We need to tackle the vignetting effect that happens from a lens. When you have a lens over a camera, because the lens is curved, the amount of light that hits the sensor isn't uniform. So at the edges, the curvature means that light has to travel through more glass before it hits the sensor, and so that makes the edges of the image darker. As you can see here, particularly in like the top corners, this effect was actually applied in post-processing. So I went looking for vignetting images, and this is a photographer who's put it back on for dramatic effect. So we thought it was a defect, but apparently we were wrong. The way to tackle this basically is you give the ISP a table of gain values, and it will use those. It's not the size of a full image, it's much smaller, 32 by 32, but the ISP will extrapolate from that table a gain for each different pixel in the sensor, and then it will apply that. And that table is just provided in the tuning files, just as the black level correction are. You can give it a few different tables. The CT here means color temperature. So lens shading is something that you can adjust for different color temperatures. So we can provide tables for 3 different color temperatures in the tuning file, basically. And then the ISP itself will interpolate between them. So depending on what the actual color temperature it is, it will interpolate a table between the 2 tables that you gave it, if that makes sense. And that takes us from the corrected black levels, particularly down in the bottom corners. You can see it's a little bit darker, and it gets a little bit lighter. This is not a very good image to demonstrate that, but that's the idea anyway. And so that's what we've done so far, basically, on the work. Future things that we'd like to do, of which there are quite a few. The ISP has a lot of other image quality blocks, particularly the spatial and temporal noise reduction and tone mapping. Those are things that could make the image quality much, much better. We've not touched those so far. There's other things as well. High dynamic range, again, that can make image quality much better, and we've not touched that so far. The big one, though, is the multi-context input. The ISP supports input from up to 8 sensors, but at the moment, the driver doesn't. It only supports a single one. Supporting this in a good way is something that's actually going to be quite hard, we think, because in the kernel today, multi-context basically looks like this. This is from Intel's IPU3 ISP, and they've got a separate graph for each different context. So they support up to 2 cameras running at the same time. And the reason that they've done it this way is because when you configure the media graph, the driver needs to know which camera you're targeting, if that makes sense. So if you want to apply a crop or something, the camera needs to know which cameras, sorry, the ISP driver needs to know which camera's input you want that crop to go to. And separating the media graphs like this was a way to do that. But does it really scale? Do we want 40 video devices in there? And that problem is only going to go worse. Nobody's having conversations around the office like, we've got enough cameras streaming now, guys. We don't need to add more, are they? So long term, we think that's not the answer. And what we'd like to do, which is not we don't have a design for it or anything yet, it's just the direction of travel that we think is right, is to move things so that we can have a separate instance of the media graph tied to a file descriptor for the media device, basically. So every time you open the media device, you get an instance of the media graph, and you can configure that independently of all the others. And we think that that would be a better way to do it, future-proof, because in theory it's unbounded. You can do as many as you like that way. But it will take a lot of work, because the infrastructure in the kernel right now isn't designed for that. So it's new APIs that we need to add, but we think that that's the way to go, basically. How can you use what we've done? Well, you can use V4L2. It's completely V4L2 compliant. So if you've used V4L2 to stream from a complex camera pipeline before, you can do it. That's kind of a demonstration of how to do it. But then you'll not get the benefits of all the image quality work that we've done, and you need to handle all the media graphs yourself, of course, and that's kind of annoying. So that's the reason libcamera exists. You should just use the libcamera. There's a few different ways to do it. You can either just use the APIs directly, or frameworks like GStreamer and Pipewire support libcamera now as well. So you can go through there, and you'll be able to use the ISP. Yeah, that's it. Any questions? Shoot, go on. Thanks, Jacopo.
I have two questions. It's a great presentation. I have two questions. The first one, you listed platforms at the beginning of your presentation where
Yes.
this ISP could be found on. So when you buy these platforms, do they come with some kind of software development kit or, to boot the board?
I don't know, but I suspect that it depends who you are.
And if you do that, what kind of driver are they using to drive the ISP?
I think they'd be using the similar things to, ARM has a reference implementation.
Oh, okay, so they would be starting from
I would expect they would start from that.
Okay. Do you have any examples of pictures that were taken with your drivers that don't have like the reference model that you have?
I don't, I'm afraid, but I can send you some.
That'd be interesting.
The development board that we have is extremely large, and the cable to the camera is extremely short. So it's difficult for me to pick it up and
Get to the bridge or something.
Well, what we need is one of the Renaissance boards, and then we can have it more portable.
Actually, not question. I'm from Renaissance, so I'm responsible for that board. So maybe we can share the board, but it's called Kakipi.
Kakip, yeah.
Kakipi. So we can share the link later. But it's not yet a website, but it's ready.
Oh, well, Kakip's got one ready with the ISP in it, has they?
Yeah.
Ah, perfect. Okay,
yeah.
Perfect. That's good. Anyone else?
Maybe just a generic question. What's the performance of that image processing? How many frames per second can you handle?
I don't remember from the specification what it is, and the development board is not a real environment. So on there, not great, but that's not representative, if that makes sense.
Okay, thanks.
If I may on this, more than frame per second, ISP are limited in bandwidth, so how many streams and of which size you can process at a single time. Usually, I think the bottleneck is more the sensor frame rate, so it's hard to, well, this is a very new ISP, it's powerful, so with 2 streams, I think you can easily hit 60 frames per second, multiple streams.
Okay, thanks.
Okay, thanks. Oh, one more, sorry.
You were talking about the image correction algorithms. Your work was to, did the algorithms already exist and you just had to make them fill up the specific structures that you added, or did you implement these algorithms? And if the last case, is this a generic for other cameras as well, or each camera has one?
A little bit of all of that, basically. So libcamera supports 4 ISPs at the moment, and they each have to have a kind of bespoke implementation of the algorithm, because they each do parameters and expect they each provide different statistics and expect different parameters back. So there is some bespokeness to it. But the implementations of the algorithms already existed in libcamera, and we've reused them, and we centralize parts of them where we can. So there is some centralization, but also some bespoke bits. Okay. Anyone else? All right. Thank you very much.